In 1.5, we are going to start looking at limits that involve infinity, either limits as x approaches infinity or where our limit value approaches infinity. Okay, so let's start by looking at a familiar graph, the graph of 1 over x, which again we know to be a hyperbola with asymptotes on the x and y axes. Okay, looks something like this. And then let's go through these limits over here. So the limit as x approaches 0 from the right. Remember, if it has a little plus sign here, it's a one-sided limit. So we are coming just from the right side, and we are going, as we get closer and closer to 0, we go up and up and up. So this is approaching infinity. Okay? And then as we approach 0 from the left, we're coming this direction, and we go down and down and down. So this approaches negative infinity. Now, because our fingers do not match if we were to trace on both sides of 0 as we move in from both sides, or because these two things are not equal, then this limit at 0 does not exist. Okay? All right. And then for these next two, we're going to look at what the function does as x approaches negative or positive infinity. So now we have infinity in the x value. So for approaching negative, now technically we could say that this is approaching negative infinity from the right, and we could put a little plus sign there. But when it's positive or negative infinity, you can only approach from one side, so we don't need those. Okay, so as we approach negative infinity, we get closer and closer and closer to 0. Okay. And then also over here on the right side, as x approaches positive infinity, f of x gets closer and closer and closer to 0 from above. Okay? Now, what we have is we have some terms that have previously been defined in ways that aren't super satisfactory, but not knowing calculus, that's as good as we can do. Okay, and those are asymptotes. We know that we have a vertical and a horizontal asymptote on this graph, and we also have this general understanding from algebra that an asymptote is a line that a curve can get really close to but not touch, except when it does, because if you remember, sometimes a function can actually pass through an asymptote, and that kind of messes with our definition. The reason for that is because we're not looking at the real definition. Asymptotes are actually defined in terms of limits. Okay? So to start, I'm going to define a vertical asymptote. Okay? And a vertical asymptote, if you look at what happened here, okay, on these two limits, a vertical asymptote is where the limit as x approaches a constant from either the left or the right, just has to be one-sided, okay, approaches positive or negative infinity. And that's actually an if and only if statement, so I'm going to write it that way, okay? So we can say that x equals c, the constant, in this case it was 0, is a vertical asymptote, okay? If and only if, IFF remembers if and only if, or you can use the double-headed arrow, if and only if the limit as x approaches c, and I'm going to put a plus or minus right here to say from the left or the right, okay? So x approaches c from either the left or the right of f of x is equal to positive or negative infinity. Okay, now in terms of identifying where an asymptote is, if you look at a function, like let's say you have 2 over x minus 4, and you say, I know it has a vertical asymptote at x equals 4, you don't have to write out the limit, okay? But this is where, like, you can still use your Algebra 2 knowledge, but this is where the limit, the definition comes from, the real definition of an asymptote, okay? And it is true that a function can never touch a vertical asymptote because we have a hole in the domain. We have a point that does not exist, okay? For horizontal asymptotes, though, it's a little bit of a different story. For a horizontal asymptote, we can say that y equals c, so the horizontal line y equals c is a horizontal asymptote if and only if, and now I'm looking at what happened here, we're talking about end behavior. So if and only if the limit as x approaches positive or negative infinity of the function is equal to that constant. okay? And so this is how we justify our or how we rectify our misunderstanding, or that little piece that has probably been bothering you and keeping you up at night for 2 years since Algebra 2, I'm sure, about how if an asymptote is a line that a function can't cross, how come sometimes a function does cross that? Like if we had something like this, okay? So a rational function could look like this, and we could say, well, something is happening right here that is causing a problem with our definition of an asymptote where the line does not, or a curve does not cross that line. And the reason is because a horizontal asymptote does not care what is happening locally. It only cares about the end behavior. It only cares about the limit at positive or negative infinity, okay? So if we think about asymptotes, horizontal asymptotes, in terms of what's happening on the very, very far left of a graph or the very, very far right of a graph, then it doesn't matter if we cross it once, twice, 500 times in the middle, okay? Now, this is just a quick review of Algebra 2 topics here. And if you remember your Algebra 2 rules about finding asymptotes, that's totally fine, and you are welcome to use those when convenient, okay? So let's say that we have a rational function, p of x and q of x are polynomials. We have a vertical asymptote if x minus c is a factor of the denominator, okay? And that vertical asymptote is at x equals c. So for example, this one right here, we would have a vertical asymptote at x equals 4 because x minus 4 is a factor of the denominator. Okay. Now, one thing I will add to that, though, is when we say is a factor of the denominator, we need to add, but not the numerator. Okay. And hopefully you're thinking, because if x minus 4 is in the numerator and the denominator, you know, along with some other stuff, then we actually have a whole. Okay? And then for horizontal asymptotes, remember we consider the degrees of the numerator and denominator. If the degree of q is greater than the degree of p, then we always have a horizontal asymptote at y equals 0. If the degrees are the same, then we take the leading coefficients of the top and bottom and we write those as a fraction, and we get y equals that fraction as our horizontal asymptote. If the degree of q is less than the degree of p, so the degree on top is bigger, then we have no horizontal asymptotes, but we do want to add if the degree of p is 1 more than the degree of q, then we have a slant asymptote. Okay, and I will tell you that your book calls this oblique. So if you see something asking you about an oblique asymptote, that's what it's asking for, is a slant asymptote. And then we divide to figure out what that is. Okay. Another thing about asymptotes, remember that if the question just says find the limit as x approaches infinity, well, you're just looking for that constant. If it says give the horizontal asymptote, you need to write it as an equation. You need to write y equals whatever that constant is. Okay.